Miyokaku once remarked that we will need to rewrite our textbooks on the beginning of the universe. Everyone has been eagerly awaiting a particular image, which has now been made public. This image from the James Webb Telescope reveals unusual processes in the cosmos that challenge our scientific understanding. Since the launch of the telescope, not only have our theories on the universe's origins been tested, but even exoplanets have begun to defy our understanding of physics, completely turning our ideas upside down. What new situations and answers can scientists discover in response to these provocations? We are currently witnessing a complete upheaval of the old rules in science. The James Webb Telescope is revolutionizing our perception of the universe, and each new image from this marvel of space exploration is groundbreaking. James Webb, the telescope's namesake, would have been proud. Webb was not a scientist but came from a business background. He understood the significance of space exploration for humanity. As head of NASA in the 1960s, Webb advanced space travel significantly, launching the Apollo program and advocating for space probes. Today, scientists are astonished by the capabilities of the telescope named after this pioneer. The images are so clear and sharp that they take our breath away. For the first time, we have complete analyses of exoplanets some thousands of light years away. The telescope is revealing to our scientific community that they have been relying on outdated findings and ideas for too long. Initially, many scientists are experiencing uncertainty and discomfort as everything they believed in may now be proven wrong. Miyokaku, a popular astrophysicist from the USA, is one researcher who is optimistic about these new developments. Kaku has long argued that our previous theories were incomplete. The inability to unite the world of subatomic particles with the world of formed matter alone indicates that we have not fully understood fundamental processes in the universe. Now, exoplanets are also breaking the laws of physics. It's astonishing. Initially, only ancient galaxies didn't fit into our cosmological models. Then came black holes and gigantic structures over 13 billion years old when the universe was supposedly in its infancy. Now, even planets defy our previous understanding. The latest images from the James Webb Telescope show exoplanets that challenge our previous ideas about planetary information. The telescope re-examined some of the strangest known exoplanets with its keen eye and unique array of spectrometers. The instruments can break down even the faintest light signals into their individual parts, analyzing traces of elements, gases, evidence of water, and parameters that reveal the size and orbits of distant planets. In the process, Webb finds more anomalies, extremes, and the craziest planets. One remarkable example of these impossible worlds that defy the rules of physics is K2-9b, an ultra-hot Neptune orbiting so close to its star that its surface temperatures are high enough to split water molecules into atomic hydrogen. The extreme proximity to its star leads to a phenomenon scientists call atmospheric blow-off, where the planet's atmosphere is literally blown away from the star. This discovery is unique among all known planetary atmospheres and presents a significant challenge. Webb finds so many exceptions and extremes that it's statistically impossible. K2-9b is so strange that it's almost impossible to classify and represents a blatant exception to all the rules we've established. Let's consider another world that terrifies scientists, WASP-76b, a giant exoplanet with iron raining from the sky on its night side. The planet orbits its star in a tidally locked orbit, resulting in extremely hot and cold sides. Metals melted and vaporized on the hot day side solidify into iron on the far side, then fall to the ground like rain. Once again, scientists are dealing with extreme conditions that impressively demonstrate the physical processes on exoplanets and raise more questions than answers. Particularly fascinating and puzzling is the discovery of planets orbiting their stars in the opposite direction to other planets in the same system. Such discoveries force astronomers to rethink theories about the dynamics of planetary systems and the forces that determine their orbits. WASP-17b is an example of such a world. This exoplanet, found as part of the wide-angle search for planets, WASP, is a huge gas giant resembling our Jupiter but orbits its star in a retrograde direction, opposite to the star's rotation. This was considered scientifically impossible according to current theories of planetary formation, which suggest all planets in a system should orbit in the same direction as they formed from the original protoplanetary disk. One theory that explains such orbits is that gravitational perturbations from nearby passing stars or other massive planets can dramatically alter a planet's orbit after its formation. Another possibility is that a gravitational dance between several large planets can push one or more into a retrograde orbit. Interestingly, we don't have to look beyond our solar system to find strange planets. In the Kuiper belt, we find the dwarf planet 2018 VG18, which scans have shown to be unusually dark and red. Webb spectrometers reveal that this planet is likely rich in complex organic compounds, which scientists call tholin. Despite its considerable size and peculiarity, 2018 VG18 remains without an official name because its exact orbit is yet to be determined. Its probable composition, rich in organic substances that are the building blocks of life, and unusual color do not match other dwarf planets in the Kuiper belt. This raises questions. Where does this planet come from? How did it form? And why is it so difficult to observe due to its great distance? Observing 2018 VG18 accurately and over a long period is extremely challenging, even with our best telescopes. It is possibly the third largest dwarf planet after Pluto and Eris, and researchers see it as a key object for understanding dynamic processes in the Kuiper belt and the evolution of the solar system. Planets without a star. Is that possible? Would you believe there are planets without a star? Planets typically form in the dust and gas disks left over from star formation, remaining gravitationally bound to their star. However, vagabond planets show that this is not always the case. These cosmic loners drift freely through space without a star. But where do they come from, and how can they survive in the hostile cold of space? Vagabond planets can form in various ways. One common method is ejection from their original star system due to dynamic interactions with other planets or close stellar flybys with gravitational forces strong enough to pull the planets out of orbit. Another possibility is they formed as isolated objects in a star-forming region but without sufficient mass to initiate nuclear fusion processes, similar to stars. This could also explain the existence of objects called jumbos, which are Jupiter mass-like objects that didn't gain enough mass to start nuclear fusion and become stars. Jupiter, the largest planet in our solar system, was just shy of the mass needed to initiate these processes. The James Webb Telescope shocked the scientific community again when it discovered 80 such vagabond Jupiter mass planets in the Orion Nebula. The bizarre aspect of this discovery is the almost unbelievable fact that these 80 planets have formed 40 binary systems, meaning 40 pairs of vagabond planets orbit each other within the relatively confined space of the Orion Nebula. This is bizarre and scientifically implausible. The sheer number of these planets may be due to the Orion Nebula being one of the most intense star-forming regions known. However, more detailed investigations showed that these objects are not truly planets but somewhere between planets and brown dwarfs in terms of mass. This suggests they are failed stars, as brown dwarfs are among the smallest stars known. But what processes in the Orion Nebula are responsible for these failed stars that act like planets, freely dancing through the cosmos in binary systems? This is another extreme challenge for our scientists. These objects likely form a class of their own, pushing the boundaries of our astrophysics. It is possible that such massive free-floating objects are much more common in the universe than we thought. They may be normal but are unusual to us because we were previously unaware of their existence. We have not been able to detect exoplanets in the depths of space for very long, and studying them has always been challenging. The James Webb Space Telescope represents a milestone in this respect. We are thrilled by these discoveries, but scientists are becoming overwhelmed by the new phenomena and impossible findings. Nothing is as they expected. As science reached an end, the James Webb Telescope was created to fill gaps in our knowledge and confirm existing theories. Instead of closing gaps, its findings are tearing new holes in what we consider truths. Some now say that the crisis web has triggered marks the end of our old science. As Mio Kaku said, we will need to rewrite our textbooks. But what should we write in them now? No coherent new answers have yet been found, and researchers are desperately seeking new explanations. Unlike its predecessor, the Hubble Space Telescope, which primarily observes in the visible and ultraviolet wavelengths, JWST is optimized for infrared observations. This capability allows it to peer through cosmic dust clouds, study the formation of stars and galaxies, and even characterize the atmospheres of distant exoplanets. One of the primary scientific goals of JWST is to unravel the mysteries surrounding the origins of the universe. By studying the light from the most distant galaxies, the telescope can provide insights into the early stages of cosmic evolution shortly after the Big Bang. This includes understanding how the first stars and galaxies formed and how they influenced the development of the universe over billions of years. In addition to studying the distant universe, JWST is poised to revolutionize our understanding of exoplanets, planets orbiting stars beyond our solar system. The telescope's sensitive instruments can analyze the atmospheres of exoplanets in unprecedented detail. By detecting the chemical signatures present in these atmospheres, scientists can infer key properties such as temperature, composition, and even the potential for habitability. The discovery of exoplanets has been one of the most exciting developments in astronomy in recent decades. Before the launch of JWST, astronomers relied on indirect methods such as the transit method, observing slight dips in a star's brightness as a planet passes in front of it, and the radial velocity method, detecting slight wobbles in a star's motion caused by the gravitational pull of an orbiting planet to identify exoplanets. While these methods have been highly successful, they primarily provide limited information about a planet's size, mass, and orbit. JWST promises to revolutionize exoplanet research by directly imaging these distant worlds and analyzing their atmospheres. This capability is particularly crucial for identifying potentially habitable exoplanets, worlds where conditions might be suitable for liquid water and potentially life as we know it. Understanding the diversity of exoplanetary systems and their atmospheres will provide valuable insights into the prevalence and conditions required for life elsewhere in the universe. Moreover, JWST's advanced technology allows it to study a wide range of astronomical phenomena beyond exoplanets and early galaxies. The telescope's suite of instruments includes cameras, spectrometers, and coronagraphs, each designed to capture different aspects of the cosmos. For example, the near-infrared camera NIRCam enables high-resolution imaging across multiple infrared wavelengths, while the near-infrared spectrograph NIRSpec dissects the light from distant objects to reveal their chemical compositions and physical properties. Another groundbreaking feature of JWST is its ability to conduct coordinated observations with other ground-based and space-based telescopes. This collaborative approach, known as multi-wavelength astronomy, enhances our understanding of complex astrophysical processes and cosmic events. By combining data from different wavelengths of light, scientists can construct comprehensive models of celestial objects, from stellar nurseries and black hole environments to the dynamics of galaxy clusters and the cosmic web. The challenges of operating JWST are significant. Its intricate instruments must operate at extremely cold temperatures close to absolute zero to minimize interference from their own heat radiation. Additionally, the telescope's large, delicate sunshield, about the size of a tennis court, protects it from solar radiation and maintains its thermal stability. These engineering feats require precise planning and execution, reflecting decades of collaborative effort among NASA, the European Space Agency, ESA, and the Canadian Space Agency, CSA. Despite these challenges, JWST has already begun to deliver remarkable scientific results. Communication between Earth and the spacecraft takes an average of 2 days. Such a delay makes it exceptionally difficult to implement quick fixes or iterative troubleshooting processes, which are often necessary. When dealing with complex technical issues, the engineering team must meticulously plan and execute each command, anticipating various scenarios and potential outcomes, unlike missions closer to Earth where engineers can swiftly send and receive commands. The long communication delay necessitates a more strategic and patient approach. Each instruction must be carefully crafted to address the known issues without causing additional problems. Considering the lengthy time it will take to confirm whether the command had the desired effect, the significant communication delay also means that the engineering team has limited opportunities to interact with the spacecraft. Every command sent must be effective and precise, leaving little room for error. This necessitates extensive testing and validation of commands on Earth before they are transmitted to Voyager 1. In addition to these logistical challenges, the spacecraft itself is over 4 decades old, Having been launched in 1977, the technology on board, although state-of-the-art at the time, is now considered ancient by modern standards. The engineering team must work with equipment and systems that were designed and built in the 1970s, which adds another layer of complexity to the problem-solving process. The harsh environment of space also takes a toll on the spacecraft systems. Voyager 1 has been exposed to cosmic radiation, extreme temperatures, and micrometeoroids for over 45 years. These factors contribute to the wear and degradation of its components, making it even more challenging to maintain and repair. Despite these hurdles, the engineering team remains dedicated to resolving the current issues. They are exploring various hypotheses about what might be causing the anomalies and testing potential solutions through simulations on Earth. This careful, methodical approach is essential given the stakes involved. Any incorrect command could potentially worsen the situation or lead to a loss of communication with the spacecraft. The team is also leveraging the redundancy built into Voyager 1 systems. Like many space missions, Voyager 1 was designed with backup systems to increase its resilience to failures. The engineering team may be able to switch to these backup systems, restore normal operations if they determine that a specific component is malfunctioning. In summary, while the challenges of diagnosing and fixing the issues with Voyager 1 are immense, the engineering team is utilizing their expertise, experience, and the spacecraft's inherent resilience to address the problems. Their meticulous and patient approach is crucial in managing the significant communication delays and the complexities of working with a spacecraft that is both incredibly distant and significantly aged. Despite the odds, their efforts aim to continue Voyager 1's legacy of exploration and scientific discovery far beyond its original mission parameters. The malfunctions might be the result of cosmic rays altering some of the spacecraft's delicate electrical systems. These high-energy particles originating from distant supernova or other cosmic events travel through space at nearly the speed of light. When they strike the Voyager, the particles can penetrate its exterior and impact internal electronic components. The longer the spacecraft is in space, the greater the likelihood that cosmic rays will have an effect on its systems. Over time, this phenomenon can lead to sporadic anomalies like the ones currently observed in Voyager 1's telemetry data. Engineers have long been aware of the potential hazards of cosmic rays to spacecraft electronics as well as human explorers, but the extent of their impact can be difficult to predict or mitigate. Despite these challenges, engineers have implemented various strategies to protect spacecraft from cosmic rays, including shielding sensitive electronics, designing redundant systems, and using error-correcting codes in data transmission. However, even with these precautions, cosmic rays can still pose a threat, particularly to spacecraft operating in deep space for extended periods of time, as in the case of Voyager 1. Although the recent anomalies in Voyager 1's data are puzzling, they are not entirely unexpected given the spacecraft's age and its prolonged exposure to cosmic rays. Engineers and scientists continue to monitor the situation and analyze the data received from Voyager 1. They are working to determine the precise cause of the anomalies and to develop strategies for mitigating their effects on the spacecraft's operations. Despite these challenges, Voyager 1 has far surpassed its original mission expectations and continues to provide valuable insights into the outer regions of our solar system and beyond. Its achievements are a testament to the ingenuity of its creators and the dedication of the team that has supported it for over 4 decades. Voyager 1's journey is a reminder of humanity's enduring curiosity and determination to explore the unknown reaches of space. As we look to the future, missions like Voyager 1 will continue to inspire and expand our understanding of the cosmos.